All right, let's get this started. Again, we're using the Chemistry 11th edition by Zumdahl and Zumdahl. And you'll notice that these lectures follow the textbook pretty well. I want you to be able to keep up with the reading and know where we are in the textbook. So the chapter headings and whatnot should be the same. So we're just starting with chapter one. Now, a slide of things that I think are useful. Now, I would prefer, and it's better for you to try to do your work without AI. However, I know most people are still going to use it. The best one to use really is the Google AI. At all costs, stay away from ChatGPT because you have to think about how AIs are programmed. Google AI will actually runs on the Google algorithm, uh, whereas ChatGPT is programmed to give you an answer at all costs. So ChatGPT will make up an answer if it can't find one. So I would suggest not using that. Let's see. Study mechanisms on YouTube. You have the organic chemistry tutor. That's a great one. You can just look up topics. On YouTube, you have three blue, one brown, and they are your study tool for all things mathematics. And so you can look up how to do certain kinds of math with them, and they'll show you. The chemistry LibreText, you can just Google those, and you can get topic by topic, and you'll also get practice problems and whatnot on that website. And then, of course, Khan Academy is always great, and you can just Google Khan Academy videos. You will notice I like to have a little fun with my slides. This one I put on here to make sure you remember that you're supposed to be reading the textbook. All of your quizzes will be based off your reading, and make sure you know what's in the syllabus. I put up a video going through it, but still, you need to know what's in there. I'm not going to be repeating to you what you're supposed to know from there. Now, I'm going to try to make these lectures as, unawkward, as not awkward as possible, but I'm used to talking to a class full of students and not a computer screen. So we'll do the best we can. But we're just going to start with an overview of chemistry. So, of course, all matter is composed of molecules. Molecules are going to be your combinations of atoms. You can see some molecules over here to the left. Your atoms are going to be your individual. A good way to look at it will be your individual elements from the periodic table. And so, if you're looking at molecules, there is an international standard for colors, where it's like your blues are going to be nitrogen, whites are hydrogen, oxygens are red. Your black molecules are carbon. And so, one of the things to keep in mind is that chemistry is done by electrons. So it's going to be the how the electrons of these molecules interact. But also, you're going to want to be watching for, you're going to want to learn chemical formulas. And so these are going to be your stoichiometric ratios of atoms in a molecule. So all that means is how many of one atom to how many of another atom. So up here at the top left, you have ammonia, and its chemical formula is an H3. So the stoichiometric ratio is one nitrogen to three hydrogens. Uh, and this one is a compound because it has more than one atom. Down at the bottom, you see an oxygen molecule. So O2, so this the chemical formula is O2. And so this one is called an elemental because it's made up of one element. It's just a molecule of the element oxygen. And of course, here you see the representation of carbon from the periodic table. You're going to want to learn how to read these. So our carbon, let's give it a typical generalized symbol would be X, and then there's your Z. Okay. Now, this will change a little bit when we get to isotopes, but I'll make sure you understand what you're looking at. Your X, of course, is whatever your elemental symbol is. So in this case, it's carbon. Your Z is your atomic number. That tells you how many protons are in the nucleus of a carbon atom. And so carbon has 6 protons in its nucleus. And keep in mind, it's the number of protons that makes up the element. And so, like, if you look at a periodic table, helium will have a 2 for its atomic number. And that means there's 2 protons in the nucleus of helium. And as you go across the periodic table and down the rows, you see they're in order 1, 2, 3, 4, 5, 6, so on and so forth. And that's just, and it's one, so the element changes. One element to the next is the addition of 1 proton. And that's what those atomic numbers mean. So you're going to want to be getting used to how to read the periodic table, uh, molecules, chemical formulas. Another thing to keep in mind is going to be that number right there. And so that's going to be your mass number. Uh, you can read it 2 different ways. So that is going to be, so carbon, for example, um, you can say that every carbon atom weighs 12.01 AMUs. AMUs stands for atomic mass units. The way you're going to be using this more often, make sure you know that each carbon atom weighs 12.01 AMUs, and you read each element on the periodic table the same way. One atom is going to weigh the mass number, atomic mass units. But the way you're going to be reading this more often, and this will make more sense as we use it, carbon is 12.01 grams per mole. And so that is the mass of 1 mole of carbon atoms. And that's going to be the most common way we use it. It's the same number. So you're going to get that mass number from your element, and that's going to be that's how many grams per mole of carbon you have when you have a mole, how many grams you have of the element when you have a mole of it. Okay, units of measurement. So we want to really make sure we know the SI units. SI, of course, I'm not going to try to pronounce it because I'm horrible at French, and it's an abbreviation for French words, but it means the international system. Um, I made a mistake. I don't know why I wrote that as silicone, but that's supposed to be a capital I. But your mass is going to be your kilogram. Length will be your meter times seconds. Temperature in Kelvin. Now, I want you to pay attention. Don't ever call this degrees Kelvin, because it's not what it is. You have degrees Celsius, degrees Fahrenheit, but then when you use Kelvin, it's just Kelvin. Amount of a substance will be your mole. The other two, like, if you take physics, you'll learn about amps. No one really talks about candelas, but it is another SI unit. There's not too many classes where I know candelas is used, but it's intensity of a light source. But you're going to be worried about kelvins, moles, kilograms, mm, sometimes meters and seconds, but not a ton. One thing to keep in mind here, this is important right here. If you're solving problems, when you're plugging numbers into an equation, make sure every single unit matches. Don't have grams multiplied by kilograms. Don't do that. Make sure you translate everything into the same units. Many times you'll be using an equation that has a constant in it, and the constant will have a set of units. Like you'll see when we get to gases, the ideal gas constant. It's easiest just to match everything to to the constant. You can change the constant if you want to. It's just you can get lost in the units of the constant sometimes. Here is a nice table of prefixes. So these are going to be your metric prefixes. So like it's like, you've heard things like the centimeter, the millimeter, uh, the kilometer or kilogram. Some that you're going to have to start getting used to in chemistry is going to be micro, which has this unique symbol here, which is a Greek letter mu. Nano, sometimes we do pico or femto. Pico, and you want to know like your nano is 10 to the negative ninth. So like a nanometer is 10 to the negative ninth meters. So 1 nanometer is 1.0 times 10 to the negative ninth meters. You can write it that way. Some of you in high school maybe learned it the other way. Another way you can write this 10 to the ninth nanometers. So you take the negative sign off the 9 equals 1 meter. So you can write it either way. These are going to be conversion factors. So you're going to want to make sure you keep this list around so you can use it when you're doing conversions. Let's see. Let's look at that micrometer because again, it's a kind of a unique unit. So 1 micrometer. So you see that Greek letter mu. That micro, that's 10 to the sixth, 10 to the negative sixth. So 1 micrometer is 10 to the negative sixth meters. So again, another conversion factor. Now there's one that's not on here that you'll see a lot in chemistry. And it has this symbol, an A with a circle over the top. That is the angstrom. And angstrom is, depends on the textbook, angstroms or picometers. But those are really going to be your measures of bond length in a molecule. And so an angstrom is 10 to the negative 10th. Okay. So that means 1 angstrom is 10 to the negative 10th meters. So I would make sure you know that one too. So if you ever see that A with the circle over the top of it, that's your angstrom. Okay. Now I did get a little overzealous. Some of the stuff I wrote up above, I had intended to write here in the blank space, but whatever. Another thing I want you to pay attention to is, so let's think about the kilometer. Okay. So you can do, if you go back up here, your kilo, 10 to the third. So 1 kilometer, you can write that as 10 to the third meters. Sometimes you'll see me in calculations, 1 kilometer is 1,000 meters. Now, 10 to the third, this is something called scientific notation. So just you make sure you know how it works. Review that, make sure you understand scientific notation and how it works. So 1 times 10 to the third is the exact same as 1,000. Okay. So I don't really care how you write it with these smaller numbers. When you're doing assignments, you want to switch to scientific notation if your numbers start getting ridiculously large or small. But otherwise, you can keep them in standard notation. There's like a centimeter. Well, centi, where's it at? Centimeter is 10 to the negative 2. So 1 centimeter is 10 to the negative second meters. Or let's see, you know that 1 meter is 100 centimeters. So again, I don't really care how you do that. I just want to make sure you notice the how those line up and that you are reviewing your scientific notation so it makes sense. All right, uncertainty in measurement. Okay, so when you're using equipment in a lab, you're going to be able to read definitely to a certain number, and then you're going to have some uncertainty. So you always want to estimate to one place of uncertainty. So let's look at this. What you see here, so on the left, you see a burette. So this is what you would use for like titrations. Now, first off, when you're reading these, you always want to read from the bottom of the meniscus. Um, your meniscus is this little dip in the fluid. So right there, you want to read there. Okay. Now it's not actually at that line. It's pretty close, but let's take a look. Okay. Now, what can I see? I can definitely see, and keep in mind your zero would be up at the top of your burette. So you can see that at least 22, and burettes are in milliliters. There we go. So you can see that at least 22 milliliters has been used, but it goes a little bit further. Now, if I know that's 22 and that's 23, and then I look in the middle, and I can see 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. So each one of those is going to be zero point 0.1 milliliters. So each one of those hash marks is zero point 0.1 milliliters to get us from 22 to 23. Now, I can see that it definitely crosses the 22.1. And so I know that it's at least 22.1, but I need to measure to one place of uncertainty, which for me is going to be, so it's not quite at that line. So what I estimate is 22.19 milliliters, where the 9 is an estimate. It doesn't quite reach that 0.2, but it's very close. So I estimated to 22.19 milliliters. So I go to the number that I can definitely see, and then I estimate one more number. Whereas over on the right, we have a graduated cylinder. And so the graduated cylinder, so if I see that's 20 milliliters there and that's 30 there, that means that each one of these tick marks is 1 milliliter. Okay. Well, that means that this iron right here is 25 milliliters. And I can see that the water is past that. So if I, so 1 milliliter. Now what I want to do is try to space this into like 10 subdivisions between your 25 and 26. And so what I estimated, I can see it's definitely 25. My uncertainty would then be zero point 0.8 milliliters. So start getting used to your measuring devices and what they show you. Look at the numbers on them. You know, it's like your burette had separations of zero point 0.1 milliliter that you can definitely see, whereas your graduated cylinder only it has separations of 1 milliliter that you can definitely see, and then you estimate the rest. Estimate to the next number. Now let's look at an exercise. Three different laboratory pieces of equipment. Okay, you have a graduated cylinder on the left, a beaker in the middle, and a burette on the far right. And so this is an exercise. So at this point, you might want to pause the lecture and try to answer these questions. Try to answer these to see how close you get. Okay, so let's look at the graduated cylinder. Again, you see the 20, you see the 30. So you know that each one of these subdivisions is 1 milliliter. And you see, so This it's a little harder to read with the actual fluid in there. You see that your bottom of your meniscus is about right there. So it's not right on the 25 line. So I estimated the graduated cylinder. I can see 25 milliliters definitely. I'm going to estimate 0.1. The beaker, you see that the subdivisions are quite a bit greater. So I see I have 600 there, 800 there. That means that that line there has to be 700 milliliters. So really all I can see with all I know definitely is that first number there, which means I'm going to have to estimate that number. So the second number is what I'm going to estimate. And I look at where it is, and since the beaker is so big, the meniscus is really not noticeable. So you're going to measure at the bottom of it right there, and you're going to say, well, so what I did is I'm like, it's not quite at 700, but I know between those two lines is 100 milliliters. So I estimated this around 680 milliliters, where the 8 is my estimate. And then on the far right, we have another burette. And again, you can see that I have 1 milliliter between there and there. So that means each one of these tick marks, oh, hang on, is 0.1 milliliters. And I can see that definitely. Now, I notice that it's past the 47. I'm measuring right there at the bottom of the meniscus. I see that it passes 47.1, but it doesn't quite reach 47.2. Let's see. And I'm sorry, I'm going to reverse that. You're supposed to be reading burettes down. Okay. Sorry, don't want to confuse you. Okay, so burettes, you're supposed to read this way. Okay, so there's your 46.1, 0.2, so on and so forth. There's your 46.5. And so you have 6, 7, 8. It's past 46.8, but it's not quite to 46.9. And so what I estimated this at was 46.8. I'm sure about that. And then I estimated to 46.83 milliliters. And so then, of course, my 3 is my estimate. Now you've seen numbers like this where we show our uncertainty uh, by adding a range at the end of the number. So here's our burette again, and you see we have the estimate of 46.83 plus or minus 0.05 milliliters. So that means it's 0.05 on either side of the 0.83. Uh, Now, of course, if we went minus 0.05, that would take it above, I mean, that would reduce it to 46, like points, would take it back down to 0.7. And now we know that it does actually cross the 0.7, but it's just the uncertainty, the mathematics of the uncertainty gives us the 0.05. So what you see here is there's a number of ways that we can calculate this uncertainty. And so one of the easiest ways to do it is you take the smallest division on your device and you divide by 2. Okay, so the smallest division, so like from there to there, is zero point 0.1 milliliters. And so what I have here, plus or minus 0.1 divided by 2 equals 0.05. So my uncertainty in this device is really going to be about plus or minus 0.05 milliliters. Now, here we see a group of measurements, so from different experiments. Okay, now we can get uncertainty across a group of measurements. And what you see here is your absolute, this is going to be called your absolute uncertainty. And it's going to be your highest value minus your lowest value divided by 2. Uh, but what you want is you want a mean value for all of your numbers there. So let's look at what mean value is. So this is going to be a statistical value. So our formula for this, move this down a bit. Let me go more general to start with. So our sum over I of all of our values divided by n, that's going to give us our mean value. So what this means for this list of values on the left, that means we're going to have sum where I equals 1 to 5 over n. And so xi, so that's your x1, 2, 3, 4, 5. That's your value n. And so the sigma, this capital sigma here, okay, that capital sigma it's a Greek letter, but in mathematics it means a sum. And so what I'm going to do is take each value and I'm going to add them all together. And so what this turns into is x1 plus x2 plus x3 plus x4 plus x5. And then I divide by n, which is our number of values. And you see that I have, well, so and you see that that'll be 5 values. And so then what you're going to do is you're going to take all of these numbers, plug them into here, add them all together, divide by 5, and you'll get your mean value. So in this case, your mean value is going to be 20.16. So try plugging all those in there and dividing by 5, and you'll get your mean value of 20.6. Now, your absolute uncertainty there. So you're going to take your highest value, which is going to be your 20.7, minus your lowest value, which is your 20.14, and subtract the 2 and divide by 2. And so what that's going to give you is your uncertainty now, 20.16 plus or minus 0.02 to show the uncertainty across all of your measurements. Okay, so again, this will be your 20.17 minus 20.14 divided by 2, and that's going to give you your 0.02. So that's another way to deal with uncertainty. All right. Now, let's say we have a group of measurements, but we actually know but we know the actual value we're looking for. To start with, let's look at some statistical formulas. So we can also use standard error as a calculation of our uncertainty. So standard error would come in when you start having more complex systems of data. And so what you end up going, so again, up here, you have each one of your x sub i's. So your standard error would be your x sub I plus or minus your standard error. So you have a couple of values here. First off, there's the formula for mean value. We did that above. Now, this middle one, you may have seen this before. This is standard deviation. Now, I will tell you this specific formulation for standard deviation is called the population standard deviation. It's just the one I'm going to throw in here. There are other formats if you're not using an entire population of numbers. So like let's say you were only using a small group of numbers. Well, there's a different standard deviation for that. But that would be something you would learn when you go into your applied statistics courses. But then from there, your standard deviation is really going to be a measure of what we call precision. So you have all your numbers. What is the overall deviation of all of your numbers? So the smaller your standard deviation, the more precise your measurements were. Okay, so in some situations, the mean value is a good approximation of the actual value. And then, of course, your standard error is going to be your standard deviation divided by the square root of your value n. So remember up here, our value n was 5. So down here, that'd be square root of 5. But let's talk about okay, let's make sure we understand what precision and accuracy are. So here we're thinking about targets. Precision is how close all of your measurements are together. Accuracy is how close all of your measurements are to the actual value. So you can say that the bullseye is your actual value. And so if you look at the very first one on the far left, all of your little circles are far apart from each other and they're not close to the bullseye, so you're not precise and you're not precise or accurate. But the one next to it, you see all of your circles are in a group. So that's precise. All of your values are grouped together closely. That's precise, but they're far away from the bullseye, so they're not accurate. Now, your third one, you see they've gotten much closer to the bullseye, so your data is accurate but not precise. You'd have a large standard deviation. Large standard deviation. Oh, and by the way, this symbol here, that's the lowercase sigma, or this is the uppercase sigma. Same letter, just upper and lowercase. And again, we use this for micro, but also your Greek letter mu is going to be your mean value. Your last one there, where all of your circles are close to the bullseye and grouped tightly together, that's both precise and accurate. So precision, the more precise, the smaller your standard deviation. Accuracy, though, you can use an average value of your percent error. So again, comes into knowing what the actual value is and using it to help you figure out how accurate your data is. Types of error. Experiments can experience random error. Random error. So first off, anything. So these pink color coded words, these are vocabulary words. This is the kind of stuff you would see on a quiz. So your random error, basically your values are probability wise, they could be too high, they could be too low. Systematic error. Systematic error is something that's wrong in your measurement or with your device or somewhere in your experiment, which means that your errors are always going to occur in the same direction. So like let's say all of your measurements were too high. That's something wrong in your system. Now, I want you to carry this into the lab. One thing that I've noticed people do in labs is instead of taking the time to actually analyze what happened in the lab, what kind of error they might have had, I will get labs turned in that say, oh, human error. Okay, well, that's a nice BS way of trying to get out of doing your work. So we're not going to do that. I don't want to see human error just thrown in. The only time you can use human error is if you can tell me what that error was, what you did wrong, and that you can document it with data. Otherwise, you need to take a shot at actually telling me what occurred and why your measurement was off. Because if I don't see that attempt and I just see human error, your grade's going to drop. So just make sure you're not doing that. Now, precision, again, can be tested using standard deviation. Accuracy can be tested using your percent error calculation. Now, again, take a look at this percent error. Your percent error is going to be your value minus the actual value, standard deviation, so you can't get a negative number, divided by the actual value times 100. So this is something you've probably used before, but now notice I've made it a little bit different. This is the average percent error. So the percent error for each one of your data points, and you could get an average percent error by doing that. So like with the numbers you had above, you could do this calculation 5 times, and then take the mean value. But that's going to take a while. When you could just calculate the mean value and get an average percent error. Now, one of the questions is, how do you know that that's a proper formula if your actual formula is this one right here? Okay, well, part of growing as a scientist is gaining the ability to make mathematical arguments and model a system mathematically. You're really going to want to be able to do this. And so we're going to go through a mathematical derivation. Now, this first one, it's going to, it can be a little intense. Some of you will be able to follow along. Some of you are going to have to practice this. That's fine. We're going to do quite a bit of this as the summer goes along, and you'll get used to it. But you need to learn how the math actually works. So, you watch the videos, keep up, take notes, and send me questions. Like if you're not sure how something worked, just ask and we'll go through it. Okay, so if we start with our general formula for percent error. So remember, and I'm going to leave off the times 100 for the moment because you can add that in back at the end. We know that in general, it's going to be each individual value minus the actual value divided by the actual value. If you're good at reading percentages as decimal points, don't even worry about the times 100. That's just to move the decimal point 2 places so that instead of 0.5, you know that that's actually 50%. But if you're comfortable with decimals, you don't have to include the times 100. But how do I know that it's appropriate then to put the mean value in here? Okay, so let's ask ourselves what a mean value is. So you remember that let's say your mean value for each one of your data points is going to be that. Now, I could do this percent error all the way up to n times. Okay, or I can just say, well, my mean value same kind of expression. Another way you can write your sum is your I is going to go from your first value to your value of n. So in this case, you remember that list above, that was 1 to 5. And then I'm going to have my percent error, each one of them. Then I'm going to divide it by the total number n. So each percent error calculation divided by n gives me the mean value of the percent error. Um, Another way you could look at this, so again, each one of these would be a percent error for an individual data point. So same idea, same kind of formula. Okay, now what we have here is in this first expression, we have a fraction in our numerator. I know that when I have a fraction in my numerator, the denominator of that fraction can come down to my denominator here. So now what I'm going to have, and for shorthand, I'm just going to do the sum over I, and you know that that's from 1 to n. That's what the shorthand means. So all I've done is brought that denominator down into the total denominator. Okay, now, one thing that you can do with sums is sums are not really worried about constants. So you can pull constants out. And in this case, 1 over n times a, that's just going to be 1 over a number times a number. That's a constant. Now I want to be careful. That's going to leave the sum of this. Now I know a is a constant. Okay. But I need to know if I have to leave it this way, if I have to leave the equation this way, or if I can uh, simplify it more. Well, we know that with sums, there's an identity that shows that the sum is distributive, which means that my sum can do this. The sum of each x minus the sum over a. Now, a is a constant. But I want to leave it this way. I want to leave it this way for a moment. Okay, so uh, this is something you'll learn as you get used to this. If I have I equals 1 to n of a constant, all I'm going to get is the my number n times the constant. Because think about it. Uh, let's say a equals 2. Okay, well, what I would have, and n equal, and you have n equal, so I equals 1 to 5, so n equals 5. And I did this, and I summed those all up, and so then I would have 2 plus 2 plus 2 plus 2 plus 2. So add it together 5 times. So then that means all you're going to have is your sum from I equals 1 to 5 of your constant a is going to be n times a. So if a was 2 and n was 5, it'd be 5 times 2. It, sit down, think about it, work it out in your head. So uh, again, what that would look like is, remember, n equals 5. That'd be a plus a. Because again, this a doesn't change. It's a constant. So that's 5 times a. So that's all that means. So you're going to get n times a out of that one. But I want to leave it like this for a moment. I'm going to bring this value of n back inside to here. Because again, remember the way fractions work, 1 over n times a equals 1 over n times 1 over a. And so I can bring one of those back inside. And what I notice is now, and I'm just going to distribute it through. So that one's going to become that minus, all right. And so I just take the 1 over n and multiply it through. Now this here should look pretty familiar. That's our mean value. So that means now that I have 1 over a, and I'm going to have my mean value minus, and you remember what we said, that this sum here just is n over a. So your sum over a is going to be n times a over n. This is now going to give, so you see here, n divided by n cancels out. 1 over a mu minus a. And now what I can do is take that and rewrite it as we were calculating the average percent error. That's going to give me mu minus a over a. And we can rewrite it with our absolute value if we want to. And you could put your times 100 back in. But what you've now done is you've said, okay, well, I've come up with a formula that gets me to here and shows that that is a correct formula, meaning that now for your data, if you want to know how accurate your data is, just calculate the mean value of all of your data, plug it into the percent error calculation, and now instead of having to do the percent error calculation n times, I only have to do it once to get an overall idea of the accuracy of my data. And so, of course, the smaller your percent error, the more accurate your data. But you just wanted to know that this is an accurate representation of calculating percent error. Now, again, go back through this, try to understand what I did. I did it step by step, like here, your sigma went to there, multiplied into there and there. That's called distribution. And so that got you this and this. So again, that's an identity of your sums. And again, when I took this value right here, that 1 over n, multiplied it into there and there. So again, not everything I did here was algebra. Okay. If you're having a hard time latching onto this, you will get used to it as time goes on. But review this. Try to understand what I did, because modeling the world around you mathematically is an important part of becoming a scientist. Okay, so here we have an example where we have 3 students measuring the length of a table that has an actual length of 1.4715 meters. So comment on the accuracy and precision of these measurements. Was there one student that had the most precise and most accurate data? Okay, well, remember, precision is standard deviation. Accuracy is going to be percent error. So I don't know, let's start looking at, let's just do standard deviations to start with. And again, you might want to pause and try to calculate these. So now let's go back up and remember what our standard deviation is. It's this expression right here. So we're going to pull that down. Now, do you see the square root? I'm going to write that differently, but I want you to take account of the fact that it means the same thing. Okay? I write it this way just because it's easier to write. So our standard deviations, let's just do standard deviation of student 1. Yep. And all we've done is we pulled down the equation from above. Now you see my exponent of 1/2? That's the same thing as a square root. Now you notice in here, though, I'm going to put a 1 on that one. That's going to be the mean value of student one's numbers, which are these numbers right here. Okay, so I also am going to want the mean value of student one, sum over, this time n equals 4, because you notice you have 1, 2, 3, 4 values. Let's see. That's going to be over each. And so again, what you're reading there, those subscripts are indices. And so what I'm saying, xi comma 1, that's each individual value, x1, x2, x3, x4, I goes 1 through 4 of student 1. And that's how you read the indices. That's each x value for student 1. So it's I comma 1. Okay, well, let's see. U1, that's going to be, and now I'm going to show you the full calculations one time. And then I want you to put in the numbers for the others. So I'm going to show you for student 1. And I want you to put in the numbers for the others and make sure you're getting the same numbers. So our mu1 is going to be 1.4717 plus 1.4711 plus 1.4722 plus 1.4715 divided by the number of measurements I took, which is 4. And so our mean value for student 1 is going to be 1.4716 meters. That is the mean value of student 1's 4 measurements. Great. Now, let's worry about this numerator of our fraction. Okay. So, because I know that n is 4, I know that. So I can just plug that in later. So let's do this sum. All right. Again, each x sub I is going to be each one of these values. Okay. So now I can't distribute the sum this time because of the square over the top of that. If you wanted to distribute that, uh, you'd have to FOIL that and get your quadratic equation, and then you could distribute the sum, or we can just leave it the way it is and plug in numbers. So again, that's going to be x1 through 4. So the first one, and here's our x1. So the first one is the 1.4717 minus the mean value, 1.4716 squared. And of course, sigma means a sum. So now I'm going to do this again for my second value, 4711 minus 1.4716 squared plus, and then my third value, so x3, 1.4722 minus 1.4716 squared. And then my fourth value, x4, 1.4715 minus 1.4716 squared. And when I use my calculator and get all this added up, this is going to give me 6.3 times 10 to the negative 7th meters. And since we're talking about scientific notation, go back through and make sure that you can you know how your calculator works with scientific notation, because some of you will have Casios, some of you will have TIs, but you don't just type in times 10 to an exponent. There's a specific button on there that will do it properly. So make sure you know how to do that. Okay, so that is that sum in the numerator of our standard deviation. Now, we can go ahead and calculate the standard deviation of student one, which is our whole formula there. And so what we're going to have, 6.3 times 10 to the negative 7th over, divided by 4, square root, and the standard deviation for student one is 3.97 times 10 to the negative 4th meters. You can write this in standardized notation. 10 to the negative 4th is 0.123 zeros, 397 meters. Because you remember your negative 4 is moving the decimal to the right, and that's 1, 1, 2, 3, 4. So I can rewrite it in its standard format. And so I have the standard deviation for student one. All right. Now, if I went through and did this whole calculation again, I need to do it for student two and student three. And of course, student two is x1, 2, 3, 4. And student three is x1, 2, 3, 4. So now you're just using the same formulas, but you're plugging in the data for each individual student. So your sigma 2 for student 2 is going to be 2.345 times 10 to the negative 4th meters, or 0.123. Well, that worked out weird. I didn't even notice that before. Okay, meters. And our standard deviation for student 3 ends up being 8.307 times 10 to the negative 4th, or 0.10008307 meters. Now let's look. Clearly, you notice that student 2 has the smallest standard deviation, which means that student two's data is the most precise. Okay. Is student two's data also the most accurate? Well, let's find out. Okay, so let's calculate the percent error for each one. Okay, well, again, I'll do student one. Mean value for student one divided by the minus the actual value divided by the actual value times 100. Okay, well, we have mu1, and that's the 1.4716. We have our actual value, which is 1.4715. And so those are the two numbers we're going to use. So what we're going to have here is our absolute value, 1.4716 minus the actual value, 1.4715, divided by the actual value, 1.4715 times 100. Student one has a percent error of 0.0068%. All right. Now, as you were doing the calculations for the standard deviation of student two and student three, you ended up getting mean values for students two and student three. To check yourself, I'll tell you what these are. Your mean value for student two is 1.4756. Student three is 1.4719. And these are in meters, but So that means that our percent error for student 2, and again, your A doesn't change. That's your actual value. So that's going to be your 1.4756 minus your value for A, 4715. So you see, now you're just using the same formula over and over again. So this is 0.279%. And if you did this again for student 3, you're going to get 0.0273%. Okay, so now let's look. Who has the smallest average percent error? Well, that's student 1. For our student 2, had the smallest standard deviation. So what can you say about the accuracy and the precision? So that you can say that student 2 is the most precise. Student 1 is the most accurate. Where's that at? Yeah. Student 1 is the most accurate. And it didn't really ask for this, but you could say that overall, oh, what? If we look at student 1, you can see that their standard deviation is not far off from student 2. So they're still fairly precise and they're the most accurate. So overall, student 1 had the best data, but there's not a single student that's the most precise and the most accurate. But you were able to find who is the most precise, who is the most accurate. And again, it's just going back to you have 3 students who did the same measurement, and it's going back to using this formula here for your accuracy and this formula here for your precision. Okay. And again, I want you to review this. Try to start wrapping your mind around the mathematics that we're doing. We'll do quite a bit more of it as the summer goes on. But yeah, this is how you would take data from these various students and analyze it. Kind of to start to understand who's the most precise, who's the most accurate. Now, I'm not necessarily going to ask you tons of questions on this in the homework, but you'll use this a little bit in your labs. I just want you to start understanding how it works. Let's see, in your labs, you might be asked for, where is it? Your plus or minus, like this. You might be asked for that once or twice. You can use the easier calculations. So it's like if you have all of your data, you can use this calculation for your plus or minus. This one here with your standard error is getting a little more intense, so we might bring that in at some point. I just want you to know it, like I want you to know it exists and be able to calculate it. If you use this one for your data in your labs, that one is the more accurate. But that's going to make you have to get your standard deviation, your mean value. This one requires the mean value. This one here is the simplest, but it's also the least accurate. So you might want to stay away from that one. This calculation here is acceptable. Using this theory here is the most accurate. Okay, so go back through this exercise. Plug in the numbers for each student. Make sure you're getting the same numbers. I got your standard deviations for precision. Your average percent errors for accuracy. Make sure you're getting that. And let's see. So we haven't done it yet, but tomorrow we'll start with significant figures, and we'll finish up this chapter, and we'll end week 1 with a little bit of chapter 2. All right, thank you.